Hey everyone, welcome back to the Veterinary Epidemiology channel. I'm really glad you're here for this one because today we're diving into a topic that I genuinely believe is one of the most important and most skipped areas in epidemiology education: sampling strategies and sample size. Here's the reality. You can apply the most sophisticated statistical model in the world, but if you started with a bad sample, your conclusions are worthless. Garbage in, garbage out. Full stop. No amount of mathematical elegance rescues a fundamentally flawed sampling approach. In this module, we're going to cover 4 probability-based sampling methods: simple random, systematic, stratified, and cluster sampling. And then we'll work through the actual math for calculating sample size. We'll do prevalence surveys, we'll do comparative studies, and we'll do disease freedom surveys. If you're sitting the NAVLE or the ACVPM board exam, I want you to know this. This material shows up. Take notes. I'll flag the high yield exam points explicitly as we go. We've got about 20 or so minutes together, so let's get to it. So why don't we just test every animal and be done with it? It's a fair question, and the answer is the foundation for everything that follows. A full census testing every single animal in a population is almost never feasible. It's too costly, too slow, and across large herds or wide geographies, it's often flat out impossible. So we sample. Here's the promise when you do it right. A well-designed sample accurately reflects the whole population, and that's what lets you make confident, generalizable inferences. That is the entire goal of sampling. But here's the part people underestimate. A bad sample doesn't just add noise, it introduces systematic bias. Your conclusions come out confidently, consistently wrong. This is where most studies quietly fail and no statistical method downstream can rescue them. Here a real-world example is selection bias. Say you only test the cows that look sick. You will overestimate disease severity every single time because the mild and subclinical cases are invisible to you. The sickest animals dominate your sample and skew every estimate upward. And notice the timing. This bias is baked in before a single diagnostic test is ever run. The quality of your sample determines the quality of your conclusions. Get this one wrong, and no amount of clever analysis will save you. Every epidemiologic study involves navigating what I call the population hierarchy. 4 levels, and every level is a potential point of error. Level 1 is your target population. This is the universe of animals you actually want to draw inferences about. Say we want to know the seroprevalence of BVD in all dairy cattle in Florida. All dairy cattle in Florida, that's our target population. Level 2 is your source population or sampling frame. This is a subset of your target population that you can actually enumerate and access. In practice, that might be DHIA enrolled herds, the farms that participate in a formal milk recording program. Not every Florida dairy farm is DHIA enrolled. Right there, a gap opens up. Level 3 is your study sample, the animals you actually select and test. Level 4 is your analyzable data, the complete usable records that survive to analysis after attrition, data entry errors, and missing values. Think of it like tasting soup. One spoonful can tell you the whole pot, but only if the soup is well stirred. If everything sinks to the bottom, your spoonful gives you a very wrong picture. The gap between target population and sampling frame is where external validity breaks down. The gap between sample and analyzable data is where attrition bias lives. Most epidemiologic errors trace back to one of these transition points, and most researchers don't map them out explicitly before they begin. Let's establish the foundation. What makes a sampling method probability-based? one simple but critical criterion. Every unit in the population must have a known non-zero probability of being selected. That property is what gives us the mathematical license to generalize from our sample back to the population. Without it, prevalence estimates are statistically invalid guesses. You cannot attach a confidence interval that means anything to them. There are 4 probability methods you need to know cold, and every one of them is fair game on the exam. Simple random sampling, the gold standard. Every animal has an equal probability of selection, but you need a complete numbered list to pull it off. Systematic sampling, you take every nth animal off a list or a line. Practical for animals moving through a chute or out of a parlor, but watch for periodicity bias if your interval lines up with a repeating biologic or management cycle. Stratified random sampling. Divide the population into homogeneous subgroups, then sample within each one. This buys you precision and guarantees that smaller groups, like rare breeds or small herds, are represented. Cluster sampling. Sample whole groups like farms or pens instead of individuals. It's the workhorse of field veterinary epidemiology, but clustering inflates your sample size needs, so you must correct with a design effect. Each method has its own use case, its own advantage, and its own failure mode. Knowing which one to reach for and when is a core competency for veterinary epidemiologists, and it is absolutely tested on board exams. To address this head on, stratified random sampling and cluster sampling are routinely confused, and I want to give you a framework that makes them impossible to mix up. The fundamental difference is this: stratified sampling. You sample from every stratum. All subgroups are represented by design. Precision goes up because variance goes down. Cluster sampling. You sample all units from only some clusters. Not every cluster appears in your study. Convenience goes up, but precision typically goes down relative to stratified random sampling because of clustering effects. Here's my memory device. Stratified equals in every group. Cluster equals some groups only. Let me show you how the same geographic variable produces completely different study designs depending on which approach you use. Suppose we're surveying cattle herds across Florida using county as our grouping variable. Stratify by county. Every single county is a stratum. We test some animals from every county in the state. Every region is represented. Cluster by county. We randomly select 10 counties, then test all farms in those 10 counties. The other 57 counties are entirely unrepresented in our study. Same variable, same geographic concept, completely different sampling logic, completely different statistical implications, and completely different conclusions you can draw. Be direct here and non-judgmental. Non-probability sampling is the reality of most clinical veterinary research. It doesn't make that research invalid, but it does constrain what you can claim. There are 3 main types you need to know. Convenience sampling. You take animals as they present. Hospital-based studies are the classic example. Sentinel surveillance herds are another. This is fast and feasible, but animals presenting to a referral hospital are systematically different from the general animal population. They're more likely to be sicker, owned by more engaged clients, and located closer to urban centers. Purposive or judgmental sampling. An expert selects animals or herds they believe are representative. This is subjective, but it can be defensible if the expert selection criteria are explicit and well documented. Snowball sampling. You identify known units and ask for referrals to others in the same network. This is genuinely useful for hard-to-reach populations. Backyard poultry flocks, non-USDA enrolled small producers, or producers with limited engagement with extension services. Here's the critical limitation, and this is non-negotiable. You cannot generate valid prevalence estimates for a defined target population from a non-probability sample. If you see hip dysplasia in 32% of laboratory retrievers at a university referral hospital, that is the prevalence in that hospital's caseload. It is not the breed prevalence. You cannot make that inferential leap without a probability-based design. Legitimate uses of non-probability sampling, pilot studies, hypothesis generation, and qualitative research. Know the distinction. Through the prevalence survey sample size formula piece by piece, because understanding each component means you can adapt it. You're not just memorizing a number. N equals z squared times p times 1 minus p divided by d squared. Z is the critical value corresponding to your desired confidence level. For 95% confidence, Z equals 1.96. For 99% confidence, Z equals 2.576. Choose this based on how certain you need to be. P is your expected prevalence, your best a priori estimate of what the true prevalence is. If you genuinely have no idea, use P equals 0.5. That gives you the largest possible sample size estimate, which is the most conservative and protective approach. D is your desired absolute precision, the acceptable margin of error around your estimate. In most veterinary surveys, D equals 0.05, meaning plus or minus 5 percentage points. Let's work through a real example. BVD seroprevalence survey. Expected P equals 0.3, desired precision D equals 0.05, 95% confidence. N equals 1.96 squared times 0.3 times 0.7 divided by 0.05 squared. N equals 3.84 times 0.21 divided by 0.0025. N equals 0.807 divided by 0.0025. N equals 323 animals. Now, we're using cluster sampling to access those animals through farms. DEFF equals 1.5, the adjusted sample size. N adjusted equals 323 times 1.5, 485 animals. Here's a question for you. What happens to N if you widen your precision from plus or minus 5% to plus or minus 10%? Because D is squared in the denominator, sample size drops by a factor of 4. Precision is expensive. Doubling your margin of error quarters your sample size requirement. That trade-off is a design decision, not a mathematical accident. Comparative study sample size comes down to 4 inputs. Know all 4. Know what happens when you change any one of them. 1. Alpha, the type 1 error rate. This is a probability of concluding there is a difference when there actually isn't, a false positive. By convention, alpha equals 0.05. Smaller alpha means you're less willing to accept false positives, and it pushes your required sample up. Power, 1 minus beta, the ability to detect a real effect. Power is a probability of detecting a difference when it truly exists in the population. The complement, beta, is your type 2 error rate, the false negative probability. Convention is 80 to 90% power. Increasing power increases sample size requirements. Effect size, the minimum clinically meaningful difference. This is the smallest difference between groups that would actually change a clinical decision. You define this before data collection. It is the most consequential number in your entire sample size calculation, and it comes not from statistics, it comes from your clinical judgment. Variance, estimated from pilot data or published literature. Higher variance in your outcome measure requires a larger sample to detect the same effect. One concept worth emphasizing here. Statistical significance is not clinical significance. A very large study can detect a statistically significant difference that is clinically meaningless. The effect size you specify is your explicit statement about what difference matters for real patients. And a note on practice. a priori power calculations done before your study are required for grant applications, ethics submissions, and peer-reviewed publication. Post hoc power calculations computed after a null result are widely considered methodologically problematic. Don't do them. Philosophical challenge that sits at the heart of disease surveillance. You cannot prove a true absolute negative. You cannot test every animal in the world and confirm that not one of them has disease. That's an impossible standard. But here's what you can do, and what the WOA framework is built on. You can demonstrate with defined statistical confidence that if disease were present at or above a specified minimum prevalence, your survey would have detected it. That minimum prevalence is called the design prevalence, P star. It is the threshold you're designing your survey to be able to detect. The formula is N equals log times 1 minus CL divided by log times 1 minus P star, where CL is the desired confidence level and P star is the design prevalence. Here a worked example is, demonstrate 95% confidence of freedom from disease with a design prevalence P star of 2%. N equals log times 1 minus 0.95 divided by log times 1 minus 0.02. N equals log of 0.05 divided by log 0.98. N equals negative 2.996 divided by negative 0.0202. N equals 148 animals. But wait, our diagnostic test isn't perfect. If test sensitivity is 80%, we adjust. N adjusted equals 148 divided by 0.8 equals 185 animals. This formula is the mathematical foundation of every WOA disease freedom declaration. When a country certifies freedom from FMD, brucellosis, or pseudorabies and attaches a specific number of tested animals to that claim, this is where that number comes from. It is not arbitrary. It is a statistically defensible confidence statement. For multi-stage herd level freedom calculations, accounting for herd level sensitivity and population structure, use epitools at ausvet.com.au. Wrap up, I want to slow down on the mistakes, because honestly, this is where good intentions go to die. Every one of these pitfalls is something I've seen in published, peer-reviewed papers. Smart people, real data, and a sampling decision that quietly undermined the whole study. So let's name them, and then let's name the fix for each one. Mistake 1, convenient sampling plus broad generalization. You test only the clinic patients in front of you, then turn around and claim your findings apply to all animals. The fix is discipline. Define your population explicitly and state the limits of generalizability clearly in the paper and in your own head before you ever write a word. Mistake 2, ignoring cluster design in your sample size. Skip the design effect and you walk straight into a chronically underpowered study. The fix is simple and non-negotiable. Always apply DEFF when you cluster. Multiply your N by the design effect, typically 1.5 to 2 in livestock work. Don't eyeball it, calculate it. Mistake 3, confusing the sampling frame with the target population. Remember the population hierarchy from earlier? This is that gap coming back to bite you. Coverage gaps silently bias your prevalence estimate, and you won't see it in the numbers. The fix, audit your sampling frame for coverage gaps. Compare frame characteristics to your target population before you sample a single animal. Mistake 4, ignoring non-response bias. And this one is sneaky in veterinary work because the farms most likely to have disease are often the least likely to participate in. Think about that. The very signal you're hunting for opts out of your study. The fix, track your refusals and compare them to your participants. Even something as basic as farm size or location on the non-participants helps you detect the bias and account for it. Mistake 5, overcounting, where the same animal gets sampled twice. It sounds trivial, but it inflates your effective N and distorts your statistical inference. The fix? Assign unique IDs and run duplicate checks. Flag and remove duplicate records before any analysis begins, not after you've already run the model. Let's land this. 5 things I want you to walk away knowing cold. 1. The population hierarchy. Target population, sampling frame, study sample, analyzable data. The gap between your target population and your sampling frame determines how far you can generalize. Know where your gaps are before you design, not after. 2. 4 probability sampling methods, 4 specific use cases. Simple random sampling for complete frames, systematic for sequential processing points, and watch for periodicity bias. Stratified for precision when you know subgroups are heterogeneous. Cluster when individual frames don't exist, and always apply DEFF. 3. Never confuse stratified and cluster. Stratified means in every group. Precision goes up. Cluster means some groups only. Convenience goes up. That distinction is exam gold. 4. Prevalence survey sample size. N equals z squared times p times 1 minus p divided by d squared. Multiply by DEFF for cluster designs. Use p equals 0.5 when prevalence is unknown. Remember, doubling D quarters your sample size. 5. Disease freedom. N equals log times 1 minus CL divided by log times 1 minus P star. Divide by test sensitivity to correct for imperfect diagnostics. This is the math behind every trade certificate and every WOA Freedom Declaration. Next module, we move into vaccine epidemiology, herd immunity thresholds, vaccine efficacy calculation, and outbreak investigation in vaccinated populations. You're not going to want to miss it. If this module helped, please hit that like button, subscribe if you haven't already, and share with others that might be interested. I'll see you in the next module.